Hey, welcome back. Today we will discuss Holder's inequality. So the statement of Holder's inequality: if x and y be two elements of L and P space, x is given here as a tuple n tuple and y is also given here as n tuple. So x and y belongs to L and P space. Now the question is that what is L and P space? So L and P space is just a norm linear space in which the norm is defined as P norm. Okay, and P norm is defined as summation of I equal to 1 to n modulus of xi to the power p and whole to the power 1 by p. Now according to Holder's inequality, summation of I equal to 1 to n and modulus of xi yi is less than or equal to summation of I equal to 1 to n modulus of xi to the power p and whole to the power 1 by p and into summation of I equal to 1 to n modulus of yi to the power q and whole to the power 1 by q. This inequality, Holder inequality, can also be written in this form, that summation of I equal to 1 to n modulus of xi yi is less than or equal to p norm of x and q norm of y, where 1 by p plus 1 by q equal to 1. Here the p and q are known as conjugate numbers. Okay, and this p and q must belongs to open interval 1 comma infinite. Now let's have the proof. So if x and y equal to 0, then the above inequality is obviously true, because if we take x equal to 0, then all the components, then all these components x1 x2 xn will be equal to 0. So if we put that x equal to 0 here, so all the components will also be 0. That's why this result will be true. So in next case, we suppose that both x and y are non-zero, and we use the lemma which we have proved in previous video, that a power 1 by p into b power 1 by q is less than or equal to a by p plus b by q, where 1 by p plus 1 by q equal to 1. So in the next step, we have, first of all, we consider this lemma, and one more thing we have to assume, or we have to take, that ai and bi must be taken in this form in order to prove this theorem. So we simply take ai equal to modulus of xi upon p norm of x whole to the power p, and bi equal to modulus of yi upon q norm of y and whole to the power q. So we take this, and in this equation, look that 1 upon p norm of x is known as normalizing constants. Okay, and similarly 1 upon q norm of y is also known as normalizing constant. So we put these values of ai and bi in equation number first here, and we simply get this result. Okay, now the above result is true for I, and hence summing up to with respect to I, here the variation of I is same in the whole equation. That's why we can take the summation on the both side. So taking summation here, summation here is not written that I equal to 1 to n, but it is understood that the variation of I is from 1 to n, because we have taken the elements from n tuples. So the variation of I will be obviously from 1 to n. So here we have taken the summation on the both side, and after that we use here the definition of p norm. Okay, the definition of p norm is just used here, and this term is written in this form. Look, these here the p is missing. Okay, here 1 by p and norm of p norm of x to the power p, and also here will be p norm of x to the power p. Here once again p must be written here, p. Okay, so once again here the p must be written here. Okay, So plus 1 upon q, look that these two will be cancelled out, these two will be cancelled out, and we simply get 1 by p plus 1 by q. Okay, and we know that 1 by p plus 1 by q equal to 1, and hence this will be 1. And now we multiply this term to 1 here, and finally we get the result. Okay, so this is